VLSos here. This is a video lesson on area under a curve. We're only going to introduce a concept here. In future lessons, this is going to lead into calculus. Let's take a look at function notation, but function notation for something specific, and it's a little more sophisticated than the function notation we would see in algebra, because we're going to put two things into the argument, a function f and a double inequality to represent a domain as an interval. So this notation stands for area under f from 1 to 3, where the A, capital A, stands for area. F is the function that we're going to find the area under. And the double inequality is the range in the domain that we're going to find the area between, which is a domain interval. Now, we're going to have and work an example. Well, for this example, we'll need to be given the function to work with. In this case, f of x will be 9 minus 2 to the x. What this notation stands for, again, is a topic called area under the curve, or as an abbreviation, AUC. And I put under in quotes because it's a little confusing. If we had a function, technically the area under that function is infinite because we can think of all of the area down to negative infinity. But what we really mean by area under the curve is the area between the curve of a function and the x-axis. AUC means area between the given function and the horizontal axis. Let's graph this situation to get a visual understanding of what this means. Now, to help graph, I'm going to draw a t-table to help me organize points. And I'm going to make my graph large by choosing 2 boxes on my graph paper to represent an interval of 1. The beginning of my interval starts at 1, so I'll choose x to be 1 and calculate y. 9 minus 2 to the 1 is 9 minus 2, or 7. And if I was to graph 7, I'm going to, on the vertical axis, make 1 box count for 2, so 7 is here. At an x value of 2, I have 9 minus 2 squared is 4, so 9 minus 4 is 5. And if I put 3 into this function, I'd have 9 minus 2 to the third is 8, which gives me a y value of 1. Those 2 points are here and here. And my curve, which is f, looks approximately like this. So what it means to be the area under the curve is the region between my bounds, the lower bound of 1, which I'll represent as a dotted line, and the upper bound of 3, another dotted line, and the area then is under the curve, but also above the horizontal axis. It's this shaded region, which has an exact area, but we don't have a geometric formula to calculate that exact area because it's not a familiar geometric shape. One of its sides, so to speak, is a curve. So the best that we're going to do right now is estimate that area, the area of the shaded region. We could guess. One way to estimate is to guess, but guessing is the least formal way of producing an estimate. So we're going to do a bit better than that. We're going to have a method or a process to organize our estimate. And the strategy for that process is to divide this complicated region into pieces such that the pieces are easy to calculate the area of, and then we could add up the area of those pieces. In other words, I'm going to make rectangles because rectangle areas are easy to calculate, and I'm going to divide this region into 4 rectangles and think of my estimate as first finding the area of those rectangles and then adding them together. Now I know that the sum of these rectangles is going to be an estimate and not exact, because visually I can see that every rectangle is going to have an area that is slightly greater than the portion of the shaded region that is enclosed by it. These rectangles peak above the shaded region here. But it's a way that I can organize my estimate. The first rectangle area is found by multiplying the height of that rectangle by its base. The bases are easy because they're 1/2, because I chose to divide up the interval into 4 equal sections, which means that the interval width of 2 has been divided into 4 equal sections of 1/2. The heights of these rectangles correspond to function values. This first rectangle has a base of 1/2 and a height of 7, because the rectangle was made by drawing a height at that function value that was found in my table. So the area of that rectangle is the height 7 times the base of 1/2, or 3 3/4. No, we're multiplying, so it's 3 1/2. The second rectangle has a height that is not in my table here, but I know that I can find that height by putting 1 1/2 into my function. And when I do, I'll get something approximate, but it is about 6. And I'm going to work with an approximate value in my table because I am producing an estimate. So I've already given 2 in an approximation. If the height of this rectangle is about 6 and the width is 1/2, then the area of that rectangle is going to be about 3. My third rectangle has a height putting 2 into the function, which is in my table, and its height is 5, times the base of 1/2 to make an area of that third rectangle of 2 1/2. The fourth and last rectangle has a height of putting 2 1/2 into my function. And again, I'm going to be working with an approximate value for the height of 3 1/2. So the fourth rectangle is a height of 3 1/2 times the base of 1/2 to give me an area of 1 3/4. These are the areas of my rectangles. And if I add them all together or sum them up, I'm using sigma to stand for the algorithm of sum. I add these 4 areas together to get 10 3/4, which is an approximation of the area under the curve. If this notation stood for the question or the project of finding the area under F on that interval, then I could say that this is approximately 10 3/4. Now there could be other methods of guessing that would arrive at an approximation very close to this. But the method of which I justified a process to produce my estimate, we will take advantage of in the future, and it will lead to being able to calculate exact areas under the curve, which is a project in calculus.